We started looking at friction a couple of days ago. Yesterday, we spent the entire class looking at friction. We established that there's two kinds of friction that can act on an object. The first kind is what we call static friction. The second kind is what we call kinetic friction. What's another term for kinetic friction? Dynamic friction, good. Sometimes, every once in a while, we call it what? Starts with an S. Sliding friction. You don't hear that name often, but it's a name that I often kind of use in my own head to help me to distinguish what we're dealing with, whether it's kinetic friction or static friction. Okay, if it's sliding, it's kinetic. If it's at rest, it's static friction. Static friction is that force of friction that keeps an object, or that tries at least to keep an object from beginning to move. Now, the weird thing about static friction is what? It's a crazy thing about static friction compared to kinetic friction. Yeah. That's right. It's more like a what? Okay, it can be bigger. Yeah, the maximum value is bigger than the force of kinetic friction. What I'm looking for here, though, is go ahead. Yeah, it can be more than one value. It's like it has a mind of its own, right? Obviously, it doesn't, but it's like it has a mind of its own. Okay, it can be whatever it needs to be. Okay, if I push on something with a force of 20 newtons, static friction can be 20 newtons sometimes. If I push on with something with 50, okay, static friction can be sometimes 50 newtons. Okay, the force of static friction can vary. It can be whatever it needs to be to a certain extent. It can be whatever it needs to be. Now, we can calculate the maximum possible value of static friction because we said it can be, to a certain extent, whatever it needs to be, up to a maximum value. Its maximum value, we'll call it SF max, say that 5 times fast, FSF max, is equal to this coefficient of static friction times the normal force. Coefficient, just a value, usually between 0 and 1, that gives us essentially a measure of how much two things stick together. Multiply that by the normal force, which for us is simply the force of gravity, at least so far. It's the force of gravity. So the force of static friction maximum is equal to mu times the normal force. But the actual value for static friction, not the maximum possible value, but the value that you actually have, isn't necessarily that value. It's either less than or equal to that value. So, for instance, if I calculated this value here, if I multiplied these two numbers together, and I got a value of 50, then this would be 50. The actual value of static friction would be less than or equal to 50. If I push on John's desk with a force of 25 newtons, okay, then it doesn't move because the maximum possible value is 50. I didn't exceed that. Static friction in that case would simply be the force that I applied, 25 newtons. If I push on it with 49 newtons, doesn't move. Okay, it's static friction because we're less than that maximum possible value of 50. What's the value of static friction? 49. That's less than or equal to 50. If I push on it with 51, what's the value of static friction now when I push on John's desk with a value of 51 newtons? 0. Because now we've got kinetic friction, right? So static friction is however big it needs to be to keep an object from beginning to move. However hard I push, okay, to keep the object from beginning to move, until I push with, or until I exceed the maximum possible value. Once I exceed the maximum possible value, then static friction is done now. It's gone. Okay, now I got to worry about kinetic friction, which is the friction of motion, the friction that tries to keep an object from, well, that tries to slow down an object, tries to make an object stop. Kinetic friction can be found simply by setting the coefficient of friction equal to the normal force. It looks almost exactly like this equation up here. The difference is that this equation doesn't give me the force of static friction. It gives me the maximum possible value of static friction. This equation gives me not the maximum force of kinetic friction, but the actual force of kinetic friction. The first one, the maximum value. The second one, the actual value of kinetic friction. Right? So I pushed on John's desk with 20, nothing happens. 40, nothing happens. 50, nothing happens. 51, well, it's no longer static friction. Now it's kinetic friction. And we're going to find the value of kinetic friction by multiplying the coefficient of kinetic friction by the normal force. Which one's going to be smaller, static or kinetic? Yeah, yeah. I kind of made that a little bit of a trick. That wasn't fair. Which force is smaller, static or kinetic? What I should have said is which force is smaller, the maximum value of static friction or kinetic. Static can be smaller than kinetic, right? The kinetic friction on John's desk when it's moving is 30 newtons, let's say. I push on it with 20. Does it move? No. What's the force of friction acting on it? 20. So static friction in that case is less than kinetic friction, right? But the maximum possible static friction is greater than the force of kinetic friction. And I know that's what you were thinking of, Dustin, when you gave my answer there. It's static friction can be bigger than kinetic friction. The maximum possible value, the value that you have to exceed to get it moving, is bigger than the force that you have to exceed to keep it moving. All right? We had some questions for homework last night. It was on a friction worksheet. You see the answers up there on the board right now, with the exception of number 6. 6, obviously, was a qualitative one and can have a million different answers. We'll take a look at number 6 in just a moment. But I just want to know before we do that if there's any other questions that we need to go over here, 1 through 5. All right, then let's have a look at 3, 4, and 5. Number 3 says, a 100-kilogram object moving at 20 meters per second comes to a stop over a distance of 40 meters. What's the coefficient of dynamic or kinetic friction between the object and the ground? So we start off in number 3 with a mass. We start off with an initial velocity, which is 20 meters per second. Final is 0 because it comes to a stop. And the displacement is going to be 40 meters. We want to find the coefficient of kinetic friction. Okay, a lot of people asked me about this yesterday as we were working on it in class. In order to get the coefficient of kinetic friction, we need to use this equation. We need to use this. Now, we don't know what the normal force is, but we can find it easily because it's just the same as m times g. This is what we're trying to find here. But we also don't know the force of kinetic friction. So we got to get that some other way. What's your suggestion? How might I find the force of friction here without using this equation because I get 2 unknowns? Yep. Okay, let's get the acceleration. Listen, this is a good question. Whenever you come across a question you're not sure exactly what to do something. But don't pick something at random. Don't say v is equal to delta d over delta t. Don't use that equation. Why not? Why shouldn't you try that one? Go ahead. Yeah, that's a group A problem, right? That's a group A equation. You're not allowed to use that unless the velocity is staying the same. Here it's changing. It's a group B problem. So we have to, if we want to find the acceleration, use one of the group B equations. Now, the one that I'd probably use is df squared is equal to vi squared plus 2ad. The f is 0. Let's take the vi squared over by subtracting. Negative vi squared equals 2ad. Now let's take the 2 and the d over by dividing. It becomes negative vi squared over 2 times d. I don't know sometimes when I do something like this if it's going to help me or not. You don't have to know that. You don't have to have a complete written in stone plan as you're doing a question. Okay? If you can find acceleration, then get it. Even if you don't know yet what you're going to do with it. Look, if you're trying the first equation and it's not working for you, you got to try something else. Get something else. Get the acceleration. Maybe it'll help you, maybe you won't. But if it doesn't help you, the worst that's happened is you've just done a little bit of extra work that didn't help you. It's okay. Don't be afraid to try something as long as it's a valid equation. You don't try v equals d over t. Try this. Hey, if it works, great. If it doesn't, oh well. Vi is 20 over 2 times 40. 20 squared is 400 divided by 80. It gives me 5.0 meters per second squared. All right. Tara suggested that I try to get the acceleration. I've got it. It's not my answer, but it's not a wrong answer either. Okay, it's not what I'm looking for, but that's okay. Maybe it helps me, maybe it doesn't. Does anybody else Have an idea of what I should maybe try to do with acceleration now that I have it? Go ahead. Yeah. Let's figure out what the force is. The only force acting on this thing is friction. So if I find the force using F is equal to m times A, that is my force of friction. F is 100 kilograms times 5.0 meters per second squared. That gives me 500 newtons. The net force is 500 newtons, but because that's the only force, the force of friction is 500 newtons. Now we go back to this original equation. The force of kinetic friction is 500, and the normal force is 100 times 9.81. So 500 divided by 981 gives me somewhere in the range, well, I guess the answer is 0.51, eh? 0.51. No units with that, because coefficient of friction just doesn't have any units. Is that okay? I love this question. Okay. Everybody knew where to start with this. Everybody in this class knew that they were going to have to use F is equal to mu times Fn. Everybody did. But a lot of people got bogged down there. A lot of people just said, well, I don't know. I get two unknowns. What do I do? Listen, if you ever find yourself in that situation again, and you probably will, you have two unknowns, then get one of them. Then find one of them. But you're going to have to find one of them some other way. Just keep trying things. As long as they're valid, sooner or later, something's going to work out for you, as it did here. Right? Any other questions with number 3 there? All right, let's take a look at number 4 now. 4 says, a hockey puck is hit on a frozen lake and is moving with a velocity of 12 meters per second. 5 seconds later, it's 6 meters per second. What's the coefficient of friction between the puck and the ice? So I've done some givens for this one. We know the initial velocity is 12 meters per second. The final velocity is 6 meters per second. We know the time interval here is 5.0 seconds. And we want to find the coefficient of kinetic friction. It's kinetic because it's sliding, right? Sliding friction. Now, I don't know how many people yesterday, as we were working on these in class, asked me the question, what's the mass? Terrence Spencer looked it up. Funny enough, the mass of a hockey puck actually varies. The acceptable range for a hockey puck is 155 grams all the way up to 170 grams. So it can vary by as much as 10%. That's quite a bit, actually. It surprises me that they're allowed to vary it that much. Okay, by as much as 10%. So I think one of them used 155. Who used 155? Okay, Spencer did. And Terry used 170. And funny enough, they get the same answer. I think Janessa used, we said, you know what, let's not use a hockey puck. Let's make it a curling rock that has a mass of about 20 kilograms, almost 50 pounds. What did you get? 0.12. Funny enough, you get the same answer. What does it tell us? You're not given a mass in this question. Why aren't we given a mass? Because it doesn't matter. Now, if you used a mass, you would have used a mass like this, right? You would have said A is equal to delta V over delta T. Okay, and you would have gotten 6 minus 12 over 5, which is negative 1.2 meters per second squared. And then you would have said F is equal to m times A. Okay, you would have multiplied whatever mass you had, 20 kilograms, whatever, times neg 1.2. And that's going to be equal to 24, neg 24 newtons. And then you're going to say the force of friction is equal to mu times the normal force. This is 24. This is 20 times 9.81. Solve for the coefficient of friction. Does that work? Sure it does. The other way to do it, if you didn't want to assume a mass, is to say the force of friction is equal to mu times the normal force. But the force of friction here is also equal to m times A. And the normal force is equal to m times g. So the masses actually cancel. That's why it doesn't matter what mass you use, because it cancels. If we rearrange that, we get mu is equal to g over a. That's 9.81 over the acceleration here, which was, what did I say it was? 1.2. And when we do the math on that one, it works out to be 0.12. No, it doesn't. Is that right? No, not 0.12. Yeah, I've rearranged that wrong, right? Should be 1.2 over, should be A over G, right? G goes down by dividing. So A was 1.2 over 9.81, which is 0.12. And there's no units. How many people got the right answer for that? Pretty good. How many people used a mass? How many people did what I just did the second time there and canceled out the mass? One or two. Okay, whichever way. They're both right. Let's take a look at 5 now. This is a good one because this is the one that's like the question that's on your quiz tomorrow. It says 100 kilogram object is at rest on a horizontal surface. There's a static friction coefficient of 0.60. There is a dynamic friction coefficient of 0.45. We push on it with 400 newtons for 5 seconds. What's the force of friction acting? The first thing you need to do here is see what the maximum possible force of friction is. FSF max is mu times the normal force. The coefficient of static friction is given to us, or is it? Yeah, coefficient of static friction is 0.60 times the normal force is m times g. It's 100 times 9.81. Multiply those together, we get 588.6 newtons. So we're pushing with 400. The maximum force of friction can be, static friction can be 588. It doesn't move. No. I push it with 400. Okay, it doesn't move anywhere because I need to exceed 588.6 to cause it to move. So if it doesn't move, then it's static friction, and the force of static friction will be whatever I pushed with, as long as that value isn't bigger than the maximum value. So it's just 400 newtons. We actually should round that to 2 digits, 4.0 times 10 to the 2 newtons. B, doesn't move. I apply a force of 650. The maximum static was 588. Does it move? Go? Yeah, it does move. So if it moves, it's kinetic friction that we have to pay attention to, not static anymore. The coefficient of kinetic friction was 0.45, and the normal force was 100 times 9.81. That gives me 4.4 times 10 to the 2. So it doesn't, it does move. When it does move, kinetic friction kicks in, and kinetic friction goes down to a value that's lower than the maximum possible value of static friction. And finally, C, how much force is required for the object to start moving? Quick answer to this one. My maximum static friction is 588. The force that's required to get it moving is 588, right? Good? You guys okay with that question? You guys going to ace the quiz tomorrow? Listen, if you're having trouble with this, ask me now. Some people are embarrassed to ask questions. It makes me look weak if I ask questions. You know what makes you look weak? Is not asking a question today and then failing the quiz tomorrow. That's what makes you look weak. Asking a question the day before the quiz makes you look strong, like you're trying to know this stuff. If you have any questions, ask them now, because I'll find out. Tomorrow I'll find out that you don't know this. Might as well let me know now. Good? All right, Dustin? It's coming. And number 6. Dustin will do it right after we do number 6 here, okay? I was counting on Dustin. 6 and 7, I guess. Provide one situation where you'd want to have a low coefficient of static friction and one where you'd want to have a high coefficient of static friction. Where would you want to have a low coefficient of static friction? There's a million examples, right? Here's the example that I used. I said, you want to push a hockey net across the ice. You guys have all seen this before, right? You go to, especially a kid's hockey game, a youth hockey game. Okay, the Zamboni's done. They put the net down, and then they go to push it to the crease. If you ever watch the referee that's pushing it across, okay, it's always harder to get it started than it is to keep it going. Okay, and that's because the coefficient of friction, there's a fairly high, well, I shouldn't say really high, but a higher coefficient of static friction between the net and the ice. Okay, we have to overcome that. Once it's moving, it's kinetic friction. That's a lower value. Okay. That's a situation where we would want to have a low coefficient of static friction. Where would you want to have a high coefficient of static friction? Yep. I'm sorry? A drag race? Yeah, that'd be a perfect example, actually, between the tires and the road, right? Yep. Okay, another one that I have that works well for me. When I come home at the end of the day, I walk in my front door, then there's the banister that goes upstairs, and then the open area that goes to the kitchen and the living room and so on. Okay, I always take my phone out of my pocket, and I set it on the banister. So the banister is like this. I set my phone literally like this. I don't know why I do that, but I do it. And it doesn't move. Okay, the rubber OtterBox case that's on my phone, between that and the oak that's on the banister, there's a high enough coefficient of static friction that it'll sit there. Okay, I'm not sure what the angle there is, but it's probably 35, 40 degrees, but yet it still sits there on that because of the high coefficient of static friction. My wife can't do that. She's got a different case on her phone. Okay, it's more of a, I don't know, more of a girly case than the rubber OtterBox case. Okay, she doesn't even, you don't even dare put her phone there because it's going to slide right off. Why? Because it's a low coefficient of static friction compared to the rubber and the oak. That make sense? You said what, sorry? No, there's not actually. No, it's like a half wall with a oak on the top. It's kind of hard to explain, but no, there's not anything on the end of it. But even still, if it slides down and hits that, it could still fall to the floor, right? So it works with an OtterBox. It doesn't work with other cases because it's the material, right? The high coefficient of static friction. Okay, what about number 7? Where would we want to have a low coefficient of kinetic friction? And where would we want to have a high coefficient of kinetic friction? I use the same example almost for low. I said pushing a hockey net across the ice. Pushing a hockey net when you're starting it, that's a result of static friction, right? But once it's moving, you also want to have a low coefficient of kinetic friction so that it's easy to push across the ice. A low coefficient of static so that you can get it moving, low coefficient of kinetic so that you can keep it moving. High coefficient of kinetic friction? Slam your foot on the brakes and you skid. The tires slide on the road. You want to have a high coefficient of kinetic friction then, right? Ladies, is that what you guys used? Okay. Yeah, nice, yeah. Good. You guys okay with that? You guys feel like you can get 100 on a quiz tomorrow? On a question like number 5? Yes? All right. Excellent. Let's move forward a little bit here, guys. We talked about free body diagrams the other day, but just briefly. We said that free body diagrams show all of the forces acting on an object. We drew one free body diagram. It was just to kind of illustrate when we were talking about different kinds of forces, how we represent different kinds of forces. Today we're going to draw more free body diagrams and actually use those free body diagrams for something other than as an end in themselves. So free body diagram, sometimes abbreviated by the letters FBD, show all of the forces that act on an object. Here's a quick example again. Okay, it's not the first one you've done, but we'll do another one here just to familiarize yourself with it again. Page 131, it says a car with a weight of 10,000 newtons. Okay, that's the force of gravity. It's coasting on a level road. There's a normal force of 10,000 newtons up. That's pretty normal, right? If you got a force of 10,000 newtons down, then you're probably going to have a force of 10,000 newtons up. Otherwise, the car's either going to move down or up. There's a force of air resistance of 2,500 backwards and friction that's 500 newtons backwards. Draw a free body diagram. So here's the car. It's kind of looks more like a little kid's car than it does a real car, but doesn't matter. There's a force of gravity of 10,000 newtons acting down. There's a normal force acting of 10,000 newtons up. Notice I have those drawn the same length because they're both the same value. I think it was Luis the other day when we drew the free body diagram that said, what about the placement of the forces? Was that you? I think it was, yeah. Could we draw the force of gravity right here instead of right there? Sure. Doesn't matter where it's drawn. As long as you have it drawn the right length and in the right direction, it doesn't matter where it's drawn. But don't draw it in both places. What else we got here? Let's assume that it's moving to the right. If it's moving to the right, then air resistance will be to the left. And it's going to be 2,500 newtons. Why did I draw the force of air resistance so much shorter than the other two forces that I have drawn so far? Scale, what about the scale? Pardon me? Yeah. But why do I have to make it accurate? Like what do you mean by making it accurate? Listen, my free body diagram not only wants to show the numbers for the forces, it should be such that one vector that's a bigger value than the next vector is drawn longer. We should be able to see without looking at numbers roughly how these vectors compare to each other. And we can see in this case clearly that force of air resistance is quite a bit smaller than the normal force and the force of gravity. All right, we got one more. We get the force of the road on the tires, friction. We'll call that FF. It's 500 newtons. Now, ideally, I'd like to make that 1/5 the length of the force of air resistance, but it's pretty hard to draw it that short, so that's good enough. It shows us that it's a smaller value. Luis, do I have that drawn in the right place? The force of air resistance, or should I have drawn it over here? It doesn't matter. No, it doesn't matter. As long as I have it drawn in the right direction, and as long as I have drawn more or less the right length. Is that good? You guys can draw these, right? That's good, because you're going to need to draw them lots today when we start doing our next thing, which is problems involving more than one force. Everything that we've done up till now, except for these free body diagrams, has always involved one force. F equals ma, that's the value of the force. Now you're going to start dealing with more than one force at once. 2, 3, 4, 15. Probably not 15, but lots of different forces acting at once. We call them multi-force problems. More than one force problems. What we want to do first when we see one of these problems involving more than one force is draw the free body diagram and then simplify it a little bit. cross off or cancel out any forces that you can, any forces that balance each other. Let's go back to that diagram that I just drew. Are there any forces here that cancel each other out that I can cross off? Gravity and the normal force are the same value. So I'm left now with just the force of air resistance and the force of friction. Draw your free body diagram, cross off anything that balances, cancel it out. You don't have to, but it does make it simpler if you do. Now what you got to do, if they're all the remaining forces, the forces that haven't canceled out, are in one dimension, and they probably will. They will for sure in the next few problems that we do. They'll all cancel out except for forces acting in the one dimension. Okay, if they're still acting in one dimension, all the remaining forces, then do the following. Add them up. Say F net is equal to the sum of the forces. So if I do a free body diagram like this, okay, here's a box, here's a force acting down, here's a force acting up, but they canceled because gravity and the normal force ended up canceling. And there was an F1 this way, and there was an F2 this way. Then I would say F net is equal to F1 plus F2. If there was an F3 this way, then I would say F1 plus F2 plus F3, and so on. Now, if one of these vertical forces didn't cancel out, we still have to add the forces together, but we're going to add them vectorially, so the problem becomes a little bit more complicated. The way that you see this written down right now isn't going to apply. We add them together, but we add them together in a different way. So for these problems, and that's what you're going to see for the next couple of days, F net is equal to the sum of the forces. All of the forces added together. Now, we also know what F net is equal to. Another value for F net goes back to Newton's second law that we learned about a couple of days ago. F net is equal to all of these forces added together, but F net is also equal to M times A. So we're going to sub in MA is equal to the sum of the forces. F1 plus F2 plus F3 plus however many forces there are. And then we're going to sub in some values and solve. At this point, though, you got to be really careful to make sure you take into account which way they're going, left or right, positive or negative. If it's going to the right, if a force is acting to the right, like F1 and F3 are, we make them both positive numbers here. If it's going to the left, like F2 is, we make it a negative value. We write it down like this, where we're adding all the forces together, but when we go to add them together, we add them as negative numbers sometimes if they're acting to the left. So it's the same thing as subtracting. Let's take a look at this example, 3.2. There's only a couple that I want to do today. This is the first one. 3.2 on 132, it says two people, A and B, are dragging a canoe out of a lake onto a beach using light ropes. Each person applies a force of 60 newtons forward on the rope. There's a force of friction acting of 85 newtons. Starting with the free body diagram, calculate the net force on the canoe. So here we don't need the acceleration, here we just need the net force. Let's draw a free body diagram, but as opposed to a free body diagram like we draw of, say, a car, where you have gravity and the normal force, let's draw the free body diagram looking at it from above. That's easier in this case. So here's my canoe. I have a force to the right, we'll call it F1 of 60 newtons. I have another force to the right, we'll call it F2 of 60 newtons. We got two people pulling in the same direction, both with a value of 60 newtons. We have a force to the left, that's friction of 85 newtons. How did I know friction acted to the left? If I pull it to the right, which way does it move? To the right. So which way does friction have to be to counter that? To the left. Okay, step one. After I've got my free body diagram drawn, the net force is equal to the sum of the forces. That's FF plus F1 plus F2. And remember what we said? The next step, step two, is to sub in MA for that. But in this case, we don't have to do that because we're just looking for the net force, not the acceleration. So F net is equal to negative 85. Why did I make it negative? Negative because it's acting which way, Tyler? Right. F1 is 60 newtons because it's positive because it's to the right. F2 is also 60 newtons, positive because it's to the right. Add those up. Hey, we're going to get 35.0 newtons. So three forces acting here, but the net force, the unbalanced force, after I take into account everything, is only 35 newtons. Intuitively, you guys know that if you pull with 120 to the right, but yet there's friction acting to the left, you don't get the full effect of the 120. You get the effect of the 120 minus whatever friction was, right? Yeah. Now again, if I was looking for acceleration, I would have just subbed in m times a right here. Okay, plugged in the value of mass and solved for the acceleration. Right, question? That's a good question. In this case, they have already done that. Okay, they've said positive is forward. Okay, so therefore, 35 newtons of positive value means forward. Sometimes I get a little careless and I don't write that. I should always write that if they don't do it for me, that positive is forward, negative is backward. Okay, but generally, the standard is forward is positive, backward is negative. So if you go with that convention, even if you don't state it, I'd probably mark it right. The only time I'd mark it wrong is if you went backwards, kind of went against the convention. Okay. But you know what? If in doubt, write it down, because it's probably a good idea to do that, even when you don't need to do it. It's probably a good idea. All right. Let's take a look at these two practice problems, please, on page 132. Those are your homework questions for tonight. In addition to what else do you have for tomorrow? Quiz, friction quiz, right? So this and your friction quiz for tomorrow. Let's get a head start on that now and see what you can get done in class here.